Assalamualaikum warahmatullahi wabarakatuh. So today our group are going to present about the experimentally which is vapor compression refrigeration. Okay, so for the introduction, refrigeration system are widely used in a daily life such as air conditioning, food storage, and industrial cooling. The vapor compression refrigeration system is the most common type due to its high efficiency and reliability. It's worked by removing heat from a low temperature space and releasing it to a high temperature surrounding. Also, the system consists of four main components, which is evaporator, compressor, condenser, and expansion valve. A refrigerant flow through this component and undergoes change in pressure, temperature, and phase. Heat is absorbed in the evaporator and rejected in the condenser. The performance of the system is evaluated using the coefficient of performance, COP. COP is the ratio of cooling effect to the work input. So the objective for this experiment is to determine the coefficient of performance, COP, for vapor compression cooling system. The scope for the experiment is one, to observe the operation of the refrigerant cycle. Second, to measure temperature, pressure, and power input. Third, to analyze the performance of the system based on collected data.
Moving on to the theory. So the theory for this experiment is that a vapor compression refrigeration system transfers heat from a low temperature region to a high temperature region with the help of external work input. It operates against the natural direction of heat flow, which is from the higher to lower temperature. The system is widely used in domestic and industrial refrigeration due to its high efficiency and reliability. The working principle is based on the phase change of a refrigerant, where the refrigerant absorbs heat during evaporation at low temperature. It rejects heat during condensation at high temperature. The system is a modified form of the reverse Carnot cycle adapted for practical operation. So the refrigeration absorbs a large amount of heat during evaporation at nearly constant temperature, and this will make the process efficient for cooling applications. Next is the COP, coefficient of performance. COP is used to measure the efficiency of a refrigeration system. It is defined as the ratio of heat removed from the cooled space to the work input. COP is the formula of COP is QL over work net in, or can also be written as QL over QH minus QL, where QL is heat absorbed in the evaporator, or in the figure we can see that it is actually Q2, and QH is heat rejected in condenser, or in figure can we see that it is actually Q1. So work net in is the net work input into the compressor. A higher COP indicates a better system performance, and the COP of an actual system is lower than that of an ideal reverse Carnot cycle due to losses such as friction, pressure drops, and non-ideal processes. Okay, so for the experimental setup, we have a refrigeration cycle demonstration unit R633 PA Hilton using R141B refrigerant fluid, as shown in the figure.
For the methodology, the first step is all valves, which were at the position of condenser, middle valve, and evaporator were open. The second step is the water supply was then started, with the evaporator flow rate adjusted to 25 gram per second, while the condenser flow rate was kept at its maximum setting. The third one is the main power supply was turned on to start the operation. The fourth one is the system was left to run for about 10 minutes until steady state conditions were reached. And then the next step is all the relevant parameters were then recorded. And then the sixth step is the experiment was repeated by varying the condenser water flow rate within the range of 35 to 40 gram per second. The next one is a total of 4 trials were carried out to ensure a reliable and consistent results. And then the next step is after completing the experiment, the main power supply was switched off. Then the water supply was shut down after a delay of 1 minute. Finally, all valves were closed and returned to the shutdown position.
So as you can see, this is our experimental result. And the experiment is starting from 25 gram per second mass flow, and we repeat by 5 times, and each time it decreasing by 5 gram per second mass flow at condenser. And we keep constant mass flow 25 gram per second at evaporator, and the pressure of condenser it increased from 165 125 kilopascal to 220 kilopascal, and the pressure of a evaporator is constant at negative 48 kilopascal by 3 times. For a fifth time, it's negative 45 kilopascal and negative 50 kilopascal. And the pressure and the condenser power input is increased from 208 watt to 224 watts, and it decreased to 220 watt. And temperature of T1 is starting from 31.2 degrees Celsius and drop to 29.4 degrees Celsius, and increase to 30.3 degrees Celsius and drop to 30.1 degrees Celsius. The temperature of T2 is starting from 29.5 degrees Celsius and drop to 27.5 degrees Celsius and increase to 29.3 degrees Celsius. And temperature T3 is starting from 32.5 degrees Celsius and drop to 31 degrees Celsius and increase until 39.4 degrees Celsius. And temperature of T4 is starting from 30.2 degrees Celsius and drop to 28.4 degrees Celsius and increase until 30 degrees Celsius. And temperature of T5 is starting from 90 degrees Celsius to drop to 80.1 degrees Celsius and increase to 90 degrees Celsius and drop to 80 degrees Celsius. And temperature of T6 is starting from 42 degrees Celsius drop to 39 degrees Celsius and increase until 45 degrees Celsius. And temperature of T7 is starting from 78 degrees Celsius drop to 61 degrees Celsius and increase until 71 degrees Celsius. And the rate of heat transfer at evaporator is in the range of 0.209 kilowatt to 0.083 kilowatt. And the rate of heat transfer at condenser is in the range of 0.1965 kilowatt to 0.5820508 kilowatt, and the COP, which is coefficient of performance, it should be decreased from 10.5556 kilowatt to 0.74074 watt. This is because we retake the first reading to make it the COP at first reading. It's 2.8333 watts.
For the discussion part, we need to find the rate of heat transfer at the evaporator and also in the condenser. And we need to use the same formula, which is mc delta T, to find these two values. The m is equal to the mass flow rate of the water in the evaporator or in the condenser. So according to the calculations result tabulated at the table 1, the magnitude of the rate of heat transfer evaporator is much lower compared to the rate of heat transfer at the condenser. Why? Because these evaporators, the heat is transferred to the refrigerants in vapor state, but in condenser, the heat is transferred from the refrigerants in liquid state. So the thermal conductivity of the most of the substance in vapor state will be lower than in a liquid state. So therefore, the magnitude of the rate of heat transfer evaporator will be lower. So this graph will show the temperatures against the SLU condenser. So for the graph of compressor power input against the SLU condensers, we will finally saw this. The refrigerant system performance is governed by the first law of thermodynamics, which is the energy in is equal to energy out. So the data show that the condenser flow rate decreased from 25 grams per second to 5 grams per second. So the heat rejections become less effective and system performance deteriorates. So the condenser heat transfer behavior like this because the heat removal become the less efficient at lower flow rates and lead to the heat accumulations on the high pressure side. And we also can find that the compressor power increased from 208 watt to 224 watts. Why? Because the more watt is required to overcome the higher condensing pressure. And also we can find that the coefficients of performance with COP dropped significantly from 2.83 to 0.74. Why this? This is because it indicates a major loss in the system efficiency. So as we of course found that the temperature behaviors which in the lower side, which T1 to T4, then remain the relative stably. Why it is because due to the constant evaporator law. But at the high side, which T6 increase as the flow rate decreases. This is because caused by the insufficient heat removal in the condenser. So finally, we can see that there is a clear inverse relationship, which the lower condenser flow rate will cause the higher compressor powers, and the lower condenser flow rate will also will cause the lower COP, which is the efficiency drop.
So this is our conclusion part, and we finally achieved the objective of the experiment, which is to determine the coefficient of performance COP for vapor compression cooling system. At the value of COP when the max flow rate of a water for condenser at 25 grams per second, 20 grams per second, 50 grams per second, 10 grams per second, and 5 grams per second are 2.8341, 10.5556, 7.1428, 5, and 0.74 respectively. So, by conclusion, we can say that the COP of the vapor compressor cooling system increase when the mass flow rate of a water at condenser is increase. And second point is, as the mass flow rate of water at condenser decrease, the compressor power input increase. And the last point is the overall temperature of vapor compressor cooling system increase when the mass flow rate of water at condenser decrease.
So, for the safety procedure, one, we need to ensure all the connection and valve are properly tightened before starting the system. Second, do not touch hot components such as the compressor and condenser to avoid burns. Third, avoid direct contact with the refrigerant as it can cause skin irritation or frostbite. Fourth, make sure water flow properly through the condenser to prevent overheating. And next, do not operate the system at pressure beyond the recommended limits. 6. Switch off the power supply before making any adjustment or when the experiment is completed. 7. Keep the working area dry to avoid electrical hazard. 8. Follow the correct startup or shutdown procedure as instructed. And lastly, report any abnormal noise, leakage, or malfunction to the instructor immediately.